In this problem, we are given the following data for a singly reinforced rectangular beam with a base of 300 mm, a height of 500 mm, a compressive strength of concrete that is equals 21 megapascals, and a yield strength of tensile reinforcement that is equals 414 megapascals, and a steel covering that is 65 millimeters. The beam is reinforced with 625 millimeters diameter bars. On the tension side only, we are tasked to determine the following: the reinforcement ratio in percent, the depth of compression concrete block in millimeters, and the design moment in kilonewton-meter. And to solve this problem, let's try to draw our rectangular beam. So since we are not given any loads, let's try to assume tension at the bottom and compression at the top. It doesn't matter where you put it because we're not given any loads. And on the tension side, we are given 625 millimeters diameter bars. We can represent this as a single steel area on this tensile side. So it has 625 millimeters diameter bars. And we are given a steel covering or steel cover of 65 millimeters. This is the distance going from the outer edge of the beam on the tension side towards the centroid of the reinforcement. This is 65 millimeters, and we are given a base of 300 millimeters and a total height of 500 millimeters. So this remaining length here, which is the effective depth of the beam, this is 500 minus 65, which is equal to 435 millimeters. Now when solve for the first problem, the reinforcement ratio is given by the formula rho equals the area of steel on the tensile side divided by B times D, where B is the base of the beam and D is the effective depth. And the total area of the steel, that is 6 times pi 25 millimeters squared divided by 4 all over a base of 300 millimeters times an effective depth of 435 millimeters. Now when solve for rho, or the reinforcement ratio, that is 6 times pi 25 squared over 4 all over 300 times 435, that is equal to 0.022569. Or in percentage, we multiply this by 100. So this is equal to 2.2569%. This is the answer for the first problem. So for the second problem, we equate the force induced by the steel, that is the tensile force T, to the compressive force, that is a resultant, equal to C. And the compressive force is just equal to the volume of this stress block that has a height of A, a width of B, and a length of 0.85 FC prime. And the tensile force T is equal to the steel area, AS, multiplied by the stress felt by steel. So we need to assume that steel will yield or not. So to simplify our calculation first, we begin assuming that steel yields. That is, the actual stress felt by steel is equal to its yield stress, or yield strength, that is Fy. So we multiply the steel area by Fy to get the tensile force T. So equating T and C, we get AS Fy equal to the compressive force, that is 0.85 FC prime, times the height of the compression block, or depth of the compression block A, times its width, that is P. And the steel area, that is equal to 6 times pi 25 squared over 4 times the yield stress that is equal to, or yield strength that is equal to 414 megapascals or Newton per millimeter squared, equal to 0.85 Fc prime of 21 times A times base of 300 millimeters. Solving for A, we get A is equal to 227.7. Now let's check whether our assumption is correct that steel is yielding by solving for actual stress Fs equal to 600 times d minus c over c. And to solve for c, we need to solve for beta. The beta factor is equal to 0.85 since our compressive strength of concrete is less than 28. And to solve for c, that is equal to the depth of the compression block divided by the beta factor, that is 0.85. So solving for c, we have c equal to 267.88. Now solving for the stress felt by steel, that is Fs equal to 600 times the effective depth d, that is equal to 435 millimeters minus c, that is 267.88 all over 267.88. Solving for Fs, we get a value of 374.32. And this value here, which is the stress felt by steel, is less than its yielding strength of 414 megapascals. Therefore, our assumption that steel yields is incorrect. Therefore, we need to revise our assumption and solve for A again. So since our initial assumption is incorrect, that is steel is yielding, we need to revise our equation. So let's try to assume that steel will not actually yield. So instead of using Fy in our equation, we will use Fs. That is the actual stress felt by the steel, which is less than Fy. So we have 0.85 Fc prime of 21 Newton per millimeter squared times A times B of 300 millimeters equal to the area of steel, that is 6 times pi 25 millimeters squared over 4 times Fs, that is 600 times d minus c over c. And c here is equal to A over beta, and for beta, given Fc prime, that is 21, this is equal to 0.85. So we have 0.85. Let's try to disregard the units to fit our equation. This is 0.85 times 21 times A times 300 equal to 6 times pi 25 squared over 4 times 600 and effective depth of 435 minus C, that is equal to A over 0.85 all over A over 0.85. So we have 0.85 times 21 times A times 300 equal to 6 times pi 25 squared over 4 times 600 435 minus A over 0.85 all over A over 0.85. Shift solving, we get A equal to 221.319 millimeters. Now let's try to check if our assumption that steel will not yield is correct. So Fs equal to 600 times d minus c over c. And to solve for c, this is A over beta. And we have A that is equal to 221.319 over B, that is 0.85. So we have A over 0.85 that is equal to 260.375. So we have Fs that is equal to 600 times an effective depth that is 435 minus C that is 260.375 all over 260.375. Solving for Fs, we get 600 times 435 minus C over C. This is equal to 402.40. And this is less than the yield strength of steel that is 414. Therefore, our assumption that steel does not yield is correct. Therefore, A, which we have solved a while ago, that is equal to 221.319 millimeters. And to compute the design moment in kilonewton-meter, we can take summation moment along the tensile force or the compressive force. And to simplify our calculation, we take summation moment along the tensile force. And the formula for the design moment, this is equal to the moment reduction factor times the nominal moment. And to solve for the nominal moment, we take summation moment along the tensile force. This is equal to 0.85 FC prime times A times B times the moment arm distance, which is equal to D minus half of the compression block, A over 2. So plugging in the known values, we have 0.85 times FC prime of 21 Newton per millimeter squared times A of 221.319 millimeters times base of 300 millimeters times D of 435 millimeters minus A that is equal to 221.319 millimeters over 2. So we have 0.85 times 21 times 221.319 times 300 times 435 minus 221.319 over 2. This is equal to 384.4. Newton millimeters. Also, this is multiplied by 10 raised to the 6. And to solve for the design moment, using this equation, the moment reduction factor given steel does not yield, this is equal to 0.65. Now to compute for design moment, this is 0.65 times Mn, that is equal to 384.40 times 10 raised to the 6 power Newton millimeters. So multiplying this by 0.65, we get our final answer that is equal to 249.86 times 10 raised to the 6 Newton millimeters. And to convert this into kilonewton-meter, we multiply this by a factor or conversion factor of 1 kilonewton per 1000 Newton and 1 meter per 1000 millimeters. This is equal to 249.86 kilonewton meters. And this is our final answer for the third problem.